Okay. Okay, that's fine. All right, everyone. So today we're going to talk about Quiz 29, which overall the scores were a little bit less than desirable, and I think that's partly due to the increased level of difficulty, but I think it's partly due to the fact that some of us were less than fully committed to the material that week. Like Derek, you were sick, right? Among other things, plus tennis. And Mo, you had everything going on, among other things. And I appreciate that all this stuff is happening, but sometimes I feel like calculus gets the short end of the stick. Like we never pull you out of other classes except for May 7th. Okay. Anyway, so we have a cone. We have a cone of radius 10 centimeters and height 5 centimeters. And it says slice it horizontally. So I'm going to first draw a cone or a slice of a cone that might look, not that, maybe this, maybe this. Here, this looks better. Okay, so here's a cross-sectional view of a cone. And from this, I want a little slice, right? And we know that the height of the cone is 5. So let's put 5 in here somewhere. 5 from there to there. And let's call this height from the base up some h. And let's call this, no, we don't have to call it anything. What do we know about this width here? How much, Johnny? I think 20. It would be 20. Okay? And I think that was part of our problem. Because it was a cone, everyone thought about it in terms of a circle first. I think if you just think of it in terms of just a little slice first, then it's easier. Okay? So think about it in 2D, then think about it in 3D, and then think about it in terms of volume. Okay, and the thickness of our slice is going to be delta H. So if this bottom distance here is H, and this top distance would be what? Alex. 5 minus H. Very good. And again, I really want to say this is not the only way to do it. This is just the way that I saw it most cleanly. Okay. So then we have a pretty good setup there. Oh, let's call this, I don't know, W for width. Let's not think of it in terms of a radius yet. Okay? Now, the problem right now is that we have things in terms of H and W, and that's too many variables. So our goal over the next couple of minutes is to try to think of a way to express W in terms of H only. Okay? And then we can start rocking and rolling. All right, well, so we can say that let's use like similar triangles. If we have one little triangle on top that's W and whose height here is 5 minus H, we can have a bigger triangle sitting next to it that is whose height is 5 and whose width is 20. So it's like Dr. Evil and Mini-Me, right? Then we're okay. We can say W is to 20 as what is to what, Tom? Let's jump in. As 5 minus H is to 5. Proportions are friends, and good friends at that. So then I can say, okay, 5W equals 20 times 5, the quantity, 5 minus H, right? So 5W equals 100 minus 20H. So W equals what? What do we have here left? Colton? So, Colton, you don't have your contacts today? Well, if this is the same prescription, I'll be amazed. Okay. Okay, so then you get 20 minus 4h. Okay, so notice, everyone, I just expressed W. That was great, Johnny. What a guy. I just expressed W in terms of H, which is good. Now, Mo, you and Colton, if you're blind, you can move up front. There's no one here. Just a thought. Okay. So this is really, really good. Now we've got it in terms of W minus 4H. So then it gets better. But wait, there's more. If W equals 20 minus 4H, what does R equal now? Yeah, 10 minus 2H, right on, 1/2 of that. So now we've got things in terms of R and H, which I think is getting us closer. So if we know that R is 10 minus 2H, the area of my slice, okay, the area of the slice up here, area, not yet volume, just area is what? Okay, equals pi r squared. And so Johnny said the area equals, instead of r, we said 10 minus 2h quantity squared times pi. Right? Tom, is that okay? Okay. Now, so let's clean that up. What does that give us then? A equals 100 minus 4h plus 4h squared, not x, times pi, right? Is it 40? 10? 20, 20, it'd be 40. Right. Okay. Back up. Minus 40h, because, yeah, plus 4h squared, all of that times pi. Okay, so that's pretty cool. Now, so then, now notice I did it just in terms of area. Now, let's go to volume of the slice. Because looking at your stuff, you guys were trying to do it all at once. And I think that hurt you. I think doing it a little bit at a time while being more tedious, yes, I think is stronger. So now we've got the volume of the slice is going to be pi times, and I'm going to leave pi out for now. And let's write this the other way. We're more used to seeing this as 4h squared minus 40h plus 100 times the thickness of the slice would be what? dH, or delta H. I'm just going to put delta H for now because that's how I labeled it, and that's how I think of these. That's how I think of these. Okay. So now we're getting even better. We have this slice that's starting to turn into a disc, right? Are we at a disc right now? Maybe I should even call it that. Because it looks like a hockey puck, right? Or a vinyl LP or something like that, because it's pi r squared, and then delta H. Okay? Who does not see that? It's really important that in your mind you can conceptualize this. Johnny? It's okay? It's really important, and I think it's important. Notice I haven't done any integrating at all yet. This is all set up, and I think a lot of you are jumping right into integration, and you're not your setup is blown. And if your setup is blown, then integration is going to be crap. So we got to deal with that. So now, let's think of this in terms of volume of the cone. So now I'm taking this, I guess it's this, and I'm integrating it from 0 to 5, and it gets smaller and smaller and smaller. But since we expressed the radius in terms of h, it will get smaller as I go up higher, which is pretty cool. So I have that, and it's going to be very cool. It's in terms of 10 minus 2h, so the higher I get up here, it's going to get smaller. Okay, and that's an important concept. So the volume of the cone is going to be the definite integral from 0 to 5 of, I will in a minute, Johnny, you're jumping ahead, of 4h squared minus 40h plus 100 pi dh. God, Alex, you're on fire. Pi dh. And then Johnny is right. The pi is just a constant, so we can pull it out of 4h squared minus 40h plus 100 dh. Now, and you don't have to do this, but if you wanted to, you can even pull a 4 out, right? You can even go pi times the integral from 0 to 5 of 4 times h squared minus 10h plus 25 dh. You don't have to. I'm just throwing this out there. So now you have 4 pi integral from 0 to 5 of h squared minus 10h plus 25 dh. And now you're ready to do the integration. What are we, 10 minutes into this? I think you all are getting in a hurry. Patience. And I know that's a lot, but it's just a thought. And Derek's already jamming on that, so that gives us 4 pi times 1/3 h cubed minus, what is this going to be? 5h squared plus 25h evaluated from 0 to 5. I should put this in parentheses here because that's outside. Okay. So that gives us 4 pi times 1/3 times 5 cubed minus 5 times 5 squared plus 25 times 5. And I'm going to put it in. I know you guys make fun of me, but minus 4 pi times 1/3 0 cubed minus 5 times 0 squared plus 25 times 0. And then you get 4 pi times, what is this, 125 over 3 minus 125 plus 125. Oh, that makes it nice, doesn't it? No. 5 cubed. 5 cubed is 125. So now I have 4 pi times, these guys take care of themselves, subtract out. Now I have 4 pi times 125 over 3 equals, what is that? 500 pi over 3 units. Centimeters cubed. Good save. And that's it. And that's my one comment is just slow down, do it baby steps, and you'll probably be better off. And then you can check your answer, at least the integral you can check on your calculator and should check on your calculator, provided your integral's right. Or geometry. Good old geometry. Should we do that, Alex? Geometry check. Volume of a cube, or cone, volume of a cone equals 1/3 big B, which is area of the base, times the height, equals 1/3. Area of the base here is pi r squared. Height is how much? I guess I should go h. Equals 1/3 times pi. The radius was 10 squared times 5 equals, oh, I can see it, 500 pi over 3 centimeters cubed. And you're saying to yourself, why didn't we just do that and skip the calculus? Because a cone is kind of ridiculous, because this is a uniform thing, okay? This is uniform, so they're easy to get the volume of. But later on, we're going to get to stuff that's undulated and weird and strange, and there are no straight-ahead geometric, yes, there are no straight-ahead geometric formulas for. And so what we're trying to do here is lay the groundwork of the technique, and then we can extend that to those nasty and interesting shapes, okay? Questions on this? And I will post this online, so if you didn't take great notes, it's okay. You can watch it later if it's helpful. Okay? So, this will be on YouTube tonight. How are we? We're 17 minutes? Oh my gosh. That's bad. That's terrible. What? I didn't know. I started recording it into it about a minute. So I'm long-winded. I got to get more snappy with this. Okay, number 2. Most people did very well with number 2. It was and I thought this was a cool problem because it's hard to tell in the beginning. It gave you pi times the quantity 81 minus h squared dh. And it said, is this a cone or a hemisphere? And what's that, Derek? Oh, it's supposed to be or. Yeah, I apologize. I had 2, Mr. Hale, they are amazingly patient. I had 2 typos on this test. It was bad. Poor Jeremy was just giving me the stink eye, like steam coming out of his ears. Okay, so cone or hemisphere, and there's lots of different ways to look at this one, and maybe I should just go really fast and get on to the last one. Maybe I'll do that, because most people didn't have problems. So this was a hemisphere with radius 9, what are these? Units. And you can see that, I want to do this fast. I don't know. I mean, you can see that really because the area of a circle is pi r squared. Okay? So the area of a circle equals pi times 81 minus h squared. So this is really a radius. Really, just like the previous problem. This is really a radius, and so we can take the volume is from 0 to 9 pi, and 81 minus h squared is a representation of the radius dx. And so that, or dh, not dx. So that would give us the hemisphere, is why that came out that way. And so if that one's a hemisphere, then the other side, part B, has to be a cone. And I'm just I'm not going to do that one for you because we got to move on. Um, right. Height, height 18. Yeah. Well, the thing to do is just realize that, and again, I will try to draw this hemisphere a little bit. So the hemisphere looks like this, and we got an expression for the radius, which gave us an expression for, again, each time we're getting a hockey puck or a vinyl LP. I like the vinyl LP thing. And that's kind of not a great drawing, but we get a little disc at the bottom of that, and we've got an expression for the radius, and we just stack up the discs until the top is really all we did. Okay? Integrating, remember the integral sign means the sum of a bunch of volumes. We stack them up. We stack them up from 0 to 9, because right here 0 to 9 looks like that, and we stack them up on top of each other, and they get smaller and smaller and smaller as we go up. Well, no, because the radius here, this expression 81 minus h squared applies to any radius, whether we're here or here or here, and the radius gets smaller and smaller. So our disk gets smaller and smaller as we go up. Okay. At any height. Good question. Thank you, Mo, for being on it. Okay, now, number 3. I knew number 3 was really hard, but I gave you all a lot of hints, but with mixed success. So we'll work through it together. And it's okay. It is okay. My new motto is, you win through losing. You learn by having a few bumps in the road, and it's okay. Okay, so the graph of this thing looked kind of funkadelic. It kind of went up like this. Yeah, it looked kind of like a dumbbell, I guess. I don't know. But the big thing about the graph is, man, it's really symmetrical. Looked, I don't know, that's not a great drawing, but looked kind of like that. And really symmetrical. I'll say symmetry across both x and y axes. Okay? So that means all we got to do is do that. Okay? Get that area right there. We're set. Why? By 4. Right. Multiply first quad area by 4, and that makes our life a whole lot simpler. Okay? So let's put some scale on here. This is 0, and this is 1, is it not? And then this was like 0.3 and negative 0.3, something like that, as I recall. Okay? And we can say then the area of our region, I guess that would work, area of the red region here, like that. The area of the red region then is equal to the integral from 0 to 1 of x cubed, and this was given, times the square root of 1 minus x squared. Well, that wasn't given specifically. I guess I skipped one step, and I shouldn't do that. No, 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 no. It's cool. No, thanks for keeping me honest, Mo. So this part here, the area of these two, I guess I'll do that. The area of, that'd be the whole thing. The y squared part, so that would be just the top part. That. Okay, the area of that would be the integral from -1 to 1 of... Nah, I don't even like that. I don't even like that. We can't do that. Cannot. Not going to do it. Okay, so we'll say that the area of the red region, okay, the area of the red region is equal to the square root of the whole thing, y squared. I'll do it like that. That way it equals y. Correct. And we can express it as a function. Okay, so the square root of y squared is y. And the square root of x to the 6th is x to the 3rd. And the square root of 1 minus x squared, we're okay there. Questions? Worries? Okay, let's go like this. Equals the square root of x to the 6th times the square root of 1 minus x squared. How about that? That's a good way to look at it. It's a good way to look at it, Mo. Okay, no. And thank you for saying that. Okay. So we're integrating from 0 to 1, x to the 3rd, square root of 1 minus x squared. And again, I really want to say the way I did this is super long, but it's kind of the only way I saw it in my head. I'm sure there's shorter ways. And you know, if you come up with a shorter way that's legit and works, I'd be happy to share it with the crowd. But I wanted you to do a trig substitution, and so I said, you may find the substitution x equals sine theta helpful. I didn't say you had to, but I was hoping you would. So, trig substitution. How are we doing we're a regular schedule, right? So we're good? Trig substitution. Okay. So off to the side here, I'm going to let x equal sine theta. Okay? And so d theta dx. So in other words, the derivative of theta with respect to x equals what? Remember Mr. Hale's little chart?
Oh, yeah, so it's from negative.
Nope.
Otherwise,
Cosine theta. That y dy dx. Oh, did I do that backwards? Dx d theta. Sorry. Okay. Wait, is that right? Because then how do I get d theta then? That shouldn't be right. I want a d. I need a. Yeah, but that's. Oh. But that's not what I want. Because if you have like y equals, 4x, you go dy dx. So dx d theta, oh God. I need a d theta, but then that's not what I had before. Because you're going to need, oh, maybe we can make it work. Okay, so then dx equals cosine theta d theta. Let's see if we can make it work. Okay, so now we've got a equals 4 times, as Alex was saying, because there's 4 parts to this. Okay? So if we integrate this from 0 to 1, we're going to have to talk about that too. We'll get the area between the curve and the x-axis, correct? Okay? So if we go 4 times that, we'll get 4 of those. So we can go 4 times. And for right now, I'm going to say my limits of integration are from a to b because they're going to change. Okay? And then we get what did we get? We said sine theta. Is that rain? God, oh God. We get sine cubed theta, because this is x cubed, right? You with me? Sine cubed theta times the square root of 1 minus sine squared theta hang on. You're jumping ahead, Derek. Don't do it. As you tend to do. I just wanted to move all this. Group. Who's there? Hey, Marissa. Even if it was, I wouldn't give him that. Alex, 125. They want you somewhere. Okay? Ms. Orozco, I've got the note here. I've got the note here. So, right, just go to every door in the school. Okay, so we got 4ab sine cubed theta 1 minus sine theta. What? Okay. But I still have a dx here, right? I didn't have my dx there. And I didn't have my dx there, so now we can put it. Okay. Times, just a second, Derek. I got to stay focused. Cosine theta d theta. But, dude, let's stay focused on the calculus, okay? All right. I'm sorry, but I just kind of hit the wall today with everybody being gone, and it's like calculus is in 4th place. Calculus is never in 4th place. Okay, now, we've got some issues here, folks. What about limits of integration? Okay. When you do a substitution like this, we've got to look at these. Okay? So, instead of 0 to 1, what are my new limits of integration? You can say arc sine 0 equals what? Zero. And arc sine 1 equals what? What? It's an angle in radians. 1. No. Pi over 2. Thank you, Tom. Pi over 2. So now we can say the area equals 4 times 0 to pi over 2 of sine cubed theta square root of 1 minus sine squared theta cosine theta d theta. Rock and roll. Now, this is where it gets fun. Okay. This is where it starts to get good. What is, hang on, notice 1 minus sine squared theta sounds familiar. Funky? Something funky. You're right, Mo. Keep going. Don't quit.
Or is it tangent?
Tom, you're close. You're closing in on it. Thank you, Tom. Tom wins. And you know why? Because he ate chocolate and shared it with the rest of us. Okay, so we have cosine theta times cosine squared theta times cosine theta d theta. Okay, now keep going. Talk to me. What can we do with this? Derek's chomping at the bit. No, no, let's simplify this. Colton, very good. Very good. Because what's the square root of cosine squared theta? Cosine theta. And cosine theta times cosine theta is cosine squared theta. Okay? Good. I love this group effort. It's a beautiful thing. So now, no, let's not. So now, and I got to this point, and I was thinking there's got to be a simple way, but I did not see a simple way to integrate this one directly. It felt like it should. It really did. I was just scouring the tables and I was thinking, is there a way to do it by parts? And maybe there is because it just feels like it should go easy, but I didn't see it. So I did a second substitution. So I said, let u equal cosine x. Okay? And you're right, Mo. And again, this thing just got huge, but it works. So I don't know. Anyway, then du, it's the cosine theta. I'm sorry. We're in theta, not x. God, what a mess. Okay, so du d theta equals the opposite of sine theta. You could use the Pythagorean identity. Say that again.
Change cosine squared theta to 1 minus sine squared, so all you have are sines, and you can integrate just sines.
You could do that. Okay, he's got a way, but I'm going to keep going with this because I know it works, and make sure yours works. Okay, Mr. Hale. Okay, so you can go du d theta equals the opposite of sine theta. And then you can go, or did I say sine x? That's too many. That's fine. That should be okay. And then du equals the opposite of sine theta d theta. And then remember that, and I got another one here. Recall that sine squared theta plus cosine squared theta equals 1, so that cosine squared theta minus 1 is going to be equal to what? Yeah, negative or the opposite of sine squared theta. And that's what I wound up using here. So then we have the integral 4 times the integral of from 0 to pi over 2. And I wrote this a little bit differently now. I said that this is cosine squared theta. I'm going to do it different. Maybe it'll be easier to see. Cosine theta quantity squared times the opposite of sine theta times the opposite of sine theta squared. Okay, check out what I did this. And I did it for a reason because I knew I needed an opposite of sine theta squared down here. Okay? So what's the opposite of sine theta squared times the opposite of sine theta? Negative times negative? Yeah, but this is to the first. Oh, crap. Sadly, we're going to have to finish this later, everyone.